Alright, as promised in the previous discussion, lecture 04A for the subsurface modeling course, I am now going to step through the walkthrough for working with histograms, PDFs, CDFs within Python. And so you can find this file right here on my GitHub account. My GitHub account specifically, you can go to my repositories and you will find under Geostats Guy, or you can find me by Michael Perch, my name. You'll find one of my repositories is Python Numerical Demos. And under Python Numerical Demos, you'll find there's a bunch of new workflows I've just put up with the Geostats Pi package, and we're going to work with the one called data distributions. And so if you go ahead and download this, if you haven't worked with GitHub before, you can just click on this button right here and you can download the zip. The zip file will give you all of this all at once. You can go ahead and grab the one file and open it up. And so if you open it up in Jupyter Notebook, now I believe I have a video just previously where I give some basics about how to get started with Jupyter Notebook, how to open things up in Jupyter Notebook. So I'll assume that you're able to get it open and that you're all installed and ready to go. And so let's go ahead and walk through this right now. So we're going to have the beginning part. I just introduced the idea that this is a simple workflow for the purpose of hands-on experience. We're going to work with data sets that are available to us. The data sets, I have links here for where to find those data sets. They can be found on the GitHub account, but in a repository where I have a variety of different synthetic subsurface data sets that we can work with. Now, as I've explained before, Jupyter Notebook allows you to build workflows using multiple blocks. And within this block right here, we have a markdown text where we're able to format it and put links and so forth and put documentation. And when you see these gray blocks, they are actual Python code. So let's go to the very first block and we'll run it. This block is installing the Geostat Pi, not installing, but just giving us access to the Geostat Pi package, specifically GSLib components, which are an effort to re-implement GSLib functionality, and the Geostat component, which is where I've actually recoded some of the heavier numerics within Python. And this is more of a work in progress, of course. We're just getting that done. If you go ahead and run that block of code, that will allow you to be able to work with it. Now, your run may have taken longer. Mine just finished. The reason being is that some of this code uses Numba package in order to do a precompile of some of the numerical methods to speed it up to more to the speeds that you would see with C code. And so now we'll also import a variety of different Python packages which are very useful. We'll use NumPy for ND arrays. We'll go ahead and use pandas for data frames for tabular data. We'll use OS so that we're able to access the working directory, set the working directory and so forth. Matplotlib, pyplot as plots, PLT, so that we're able to do plotting with it, and then SciPy for various summary statistics. And so we'll go ahead and run that block. That should go super fast. Now, I like to set a working directory whenever I have a workflow. And the reason being is that maybe you want to load data from one directory, you want to save data to another directory, you want to organize it that way. You can go ahead and do that. Now, if you've launched the Jupyter Notebook from a specific directory, then that should be your current working directory. And if you have all your files there, you can skip this step, but I'll go ahead and run this step. And so now on my C drive, in my PGE 383 examples directory, I'm now working. And I'll have a data file there. Now, as shown previously at the top, you can find this specific data file at a location on the GitHub repository. Now, I've done something kind of funny for this first time. I said, hey, what if I give you the wrong name for this data file? And I think it's good to fail in front of students. I think it's good to run into errors. Let's just get a little bit of insight about what happens in Jupyter Notebook when you give yourself an error. And so I've done that. Now look at that. I simply took the name of the data file and I put cow in there. I used to work with cows when I was a kid. I was from a farm. And I put cow there just for fun. And that file does not exist. Look at the length of the error I got. So what does this tell us about Jupyter Notebook and errors? It tells us that when you get an error, it provides what many programmers or coders will know about, which is called a trace. The trace is telling you from the moment things went wrong and back to the point where you ran the command, what was the code doing? What were the different programs that were being, or algorithms that you were entering into, subroutines or objects that were made? It's providing you enough information that you could go down the rabbit hole and figure out exactly what went wrong with your code. And if you're a developer, you love the trace. The trace is very helpful to help you do debugging. Now, you're perhaps not a developer, and so you don't love the trace as much. You think, why would I get all of this? And so what you do is you just scan through to the very end, and at the very end you'll see the final error, and that is the file does not exist. This file does not exist in the working directory. Okay, fair enough. So we gave ourselves an error. We talked about traces just from the standpoint of don't be intimidated by all of this output. Recognize it's just trying to tell a programmer where they need to go, what code to look at, and so forth, to give them information to support their detective work of finding the bug. For you, just go ahead and go to the bottom, see what the error is. Now I changed the name. The name is now correct. Aha. We ran the code and we don't have any error. Nothing happened. This command of taking a CSV or comma delimited file and reading it directly into a pandas data frame, the pandas package data frame objects, does not have any output. It's simply going to turn it into a data frame with the name df. And so now df is our data frame. Now, you don't have to take that at faith. You don't have to just believe that that happened. In fact, what we'll do down here is we got two separate commands we can use. The first command is we say df.ilock. Now, .ilock is a built-in member function within data frames. Now, you excuse me, Python people, I'm talking like a C++ coder because I have many years of working in C++. You may not call it that, but it's a function built into data frame that allows you to take and slice parts of the data frame. And what I'm saying is give me the first 0 through 4 rows. That's how this slice works. And this says give me all of the columns and print them. Now, you can also use the head command, which is very straightforward, another built-in command to data frames. And we tell it, give us the first 13 rows. And if we do that and we just look at the output, okay, for my first command, I got 0 through 4 rows from my data frame. Aha, things look great. I got an X, a Y, facies, porosity, permeability, acoustic impedance. Now, this original comma delimited file is super easy to look at. You could just open it up in TextPad or any type of text editor, and you would immediately see that it has the same data, just comma delimited. Now we can also look at the head command. I like that. It's super clean code. It shows you the first, now I said 13, it's actually 0 through 12, and that's something to get used to with Python, is that it always starts at 0, whereas Fortran will start at 1 through n. Python always goes from 0 to n-1. And so we got 0 through 12 records, which are 13, the first 13 samples. Okay, so you'll see these are both the same thing. Now, you might want summary statistics for what you're working with, and so that might be useful to you. And so you can go ahead and calculate this. Now, I think there's a little bit of an error right here, if I remember right. Anyway, just on the units, but let's not worry about that too much. So we can get summary statistics. So built into data frames, once again, is a describe function. And you put parentheses around it because you can have different parameters or arguments that are passed to describe to tell it what to do. We'll just say, just do the default, just give us summary statistics. And I use the transpose command because I want to flip it X for Y, so I think it's more readable. Many people like to do it like this. That way with transpose, I get the actual values on the rows and I get the statistics on the columns. You could remove the transpose command, which would be very straightforward, and see what happens. If we do that and rerun it, look, we just flip the table, but it's the same information. So it's not a big deal. Now, anytime you want to undo, you can do a Control-Z back in the field, and you'll get back to what you had before. That's your friend. Many times you'll make an error, you need to undo something. In the Jupyter Notebook, the undo will work independently within each one of your blocks, and so it's pretty useful. Okay, So now we might want to do a variety of different things with this data frame. We've loaded it in. We want to do some summary statistics. That's very useful to us. And so what you can do is if you use the command data frame and the name of one of these columns, it will in fact return a pandas series. Now if you put the values variable afterwards, what it'll do is it'll only give you the ND array, which is a NumPy ND array. So you don't get all the information of the series, you just get an ND array. And it's very nice because ND arrays have all kinds of neat functions built into them that you can work with. For instance, you can take an ND array and you can calculate the minimum, the maximum, the standard deviation. I noticed I doubled that up, so I just removed that line. So we go ahead and run that. We run that line, we'll get this output right here. We got the minimum, the maximum, the standard deviation. We calculate the averages and so forth. There's so many different things that we can do. Now, we can also go ahead and we can use, instead of using the built-in functionality to data frames, we can actually work directly with built-in functionality for NumPy, which allows to do summary statistics directly on ND arrays. And this is pretty powerful. So remember, every time we do df, our data frame name, the name of the column, dot values, we've just returned an ND array. And so we can pass that through to NumPy dot a min, a max, and so forth. And all of these commands will calculate summary statistics for us, even up until percentile values, which is super powerful. We can get a bunch of different percentile values. We can calculate the median, skew, mean, so forth. We can do all kinds of summary statistics. And so we go ahead and run that. We've got the minimum, the maximum, the range, the P10, the P50, the P90, the P13, my favorite percentile, the median, excuse the spelling there, and the mean. And so this is pretty useful to us. We can go ahead and get those statistics. And so anytime we have a data set, we can calculate whatever summary statistics either by using built-in functionality from the data frames or built-in functionality from NumPy by extracting an ND array and working with it. So lots of different things we can do. Now you might also be interested in trying to use weighted statistics. And when we get into declustering, you'll need to be able to do this. And what's very powerful about the NumPy statistics like average is you can pass on the ND array, all the porosity values, and then you pass on a weighting array that has the same length of that ND array with the variable, and you can get the weighted statistic. And now in this case, I looked up the length of a data frame just using the len command. Give me the length, ND is the length. Then I used NumPy to say, give me a ND array full of ones with the size of ND and assign it to the name weights, WTS. And if I go ahead and run this, I've now calculated a weighted average as 0.15. Now you'll notice that that's the same as the average we calculated before because of the fact that we used equal weighting. We said all the weights are equal to 1. We could substitute the weights with any values such as declustering weights. Okay, so we were able to calculate a weighted distribution. Now, let me just demonstrate that. One thing I could do is I could say, okay, let me take the porosity values as an ND array. Let me go ahead and check. Every time we have a porosity value greater than 0.13, multiply that existing weight, the product sign or the star sign equal means multiply it by 0.1. And so we're now going to scale down those weights for every case in which the porosity values are greater than 13. And we'll rerun it with those new weights and we'll just check to see if we get, in fact, a change with the weighted. Now look what happened. Now we have a weighted mean porosity of 0.112 because we put less weight on the higher porosity values. Pretty straightforward stuff. Now, it also turns out that SciPy, one of my favorite packages, has a whole variety of handy summary statistics that we can work with. And so we can go ahead and use their statistical methods, such as the describe method from them, and we can go ahead and calculate a variety of different statistics. Now, it'll come out to us in a big array of values. And what's really cool is we can go ahead and assign those outputs to an array. So this is now an array of statistic called poor stats. And we can access parts of it by using the index of the specific statistic. And so if you want to run a bunch of statistics, but you've got to store them in a program or use them elsewhere, you can go ahead and use the indexing. Here we're taking the 6th statistic because it goes from 0 on, and we're going ahead and storing it or printing it, but we could store it and use it elsewhere. So let's go ahead and run this command. And there you go, you can see it. The SciPy routine described gives us this array of statistics. And so you have the statistics name and the values, and you can access a specific value. So the prostate kurtosis is negative 1.56. Here it is right here. And we accessed it by using the index 5. So statistic 0, these two are together in a tuple. So that's 1, 2, 3, 4, and 5. And that gave us that statistic. You notice I use the round command. I use it all the time so we get something cleaned up that way it's easier to visualize. Okay, so let's talk about plotting distributions. Now, let me just say right up front that we could have just started with matplotlib and we could have started building histograms. Now what I've done, I've re-implemented the GeoSlib hist program in Python by basically just encapsulating within a function all of the different parts I would need in matplotlib to get a histogram that looks very similar to and has the same parameters as used within GeoSlib. This is a bridge to help people get started with distribution and other types of plotting within Python who maybe just have very little experience with Python but know something about GeoSlib methods or want to work with those very simple approaches. Let's look at what my hist function does. His function just simply expects the following parameters: an array with the values, so an ND array, the min, the max value, is it log scale, is it cumulative or not, 0 or 1, 1 for cumulative, the number of bins, the weights, this would be an ND array with the weights the same size as the original array. If you don't put this in, it's fine, it'll just assume no weighting, the X label value, the title, and you can write it out immediately to a figure with nice high resolution to put into a paper. And so let's go ahead and we'll run that command. Now all we got to do is set the min and max value. We'll put right in here that we don't want log scale. It's going to be regular linear scale. We want it to be a PDF or a histogram, I should say, not cumulative. The number of bins are 10. The weights, no weights at all. And the labels for all of the axes. So we go ahead and we run that command, and what do we get out? We get this. Now it's pretty straightforward. It's super easy. If you look, there's now also going to be a graphics file in your working directory, a nice high resolution you could put into a paper. And so we have our distribution. Now, of course, at any point you could rerun it. You could change any of the parameters. I changed it to 20. That actually looks a little better. Maybe I should have done that originally. Change it to 30 bins. Oh, it's still good, eh? And it doesn't look too noisy, in fact. Like, that may actually be a good number of bins. I'm probably getting to the point now where, okay, 50 and so forth. So you can see pretty straightforward to change this and to get and look at the distribution. What's going on? Well, it looks pretty bimodal. We got two humps here, kind of like a camel or something. And so there's the possibility we have two distinctly different populations that are being mixed together. So of course we can go ahead and plot and look at a variety of different bin sizes like I just did. Here's a variety of bin sizes, more bins, less bins, and fewer bins. Now, if you get to very few bins, you're getting to the point where you really can't see too much, right? Boy, I could push that and just make that 3 bins, and now look at that. We're getting to a point where all the data are in a single bin, basically, or very few bins. You're hiding a lot of information. You're smoothing things out. So, what about cumulative plots? How do we do that? Well, we could set the cumulative of true and go ahead and rerun this. And if we do that, we'll get something like this. Looks pretty good. Now, I mentioned before that the cumulative distribution intrinsically really doesn't have a binning, but in this program implementation, it is working in a bin manner. You don't have to, but what I would suggest is just use enough bins that you can see the true resolution. It's the way I coded this up. It can be done differently. Now, as I mentioned before, I don't want to convince you that matplotlib is too hard to use. I just want to convince you that to do the same thing we just did, it would take this much code as opposed to one line of code with all the parameters that we are used to working with. And I just thought it was easier to just get people started with running it using a single line of code. I find it convenient to have handy functions I can use like that to kind of can it all up for me. But if you run this, look what you get. You get a CDF calculated for you, and it's really nice. It's quite easy to interpret, to look at. You've got all of the axes labeled, everything's nice and clean, but it took quite a bit more code to do that. Now I should note with the CDF, we are using bins right here. I've set bins right here. I wouldn't be worried about that. Look what happens if we change it to 1,000 bins and you rerun it. It doesn't change it at all, because in this implementation, when we go directly to matplotlib, what you'll find is that it in fact does not worry about the number of bins. This is a continuous representation, an unbinned representation of the CDF. Every one of these steps would be another data value, incrementing up a bunch of little increments all put together, you get the CDF. So, of course, it's very powerful if you go back directly to the matplotlib, because then you're able to have complete control over the distributions, the display of the values, and so forth. And there's a lot, you can actually get pretty fancy with it. Of course, I don't want to neglect, there's a lot of other statistical display type of methodologies, ggplot2, Seaborn, and so forth. But for starters, it's a nice idea to just start with these very basic approaches. Now we can round out everything by going and looking at all of the possible data we have within our data file and plotting their distributions. And we see the nice bimodal porosity, and we look at the faces and we recognize that, I know what's going on. If we color coded this, we'd probably find out that these are two distinct faces. We won't do that right now, but it'd be pretty straightforward. We can also look at the permeability, see what's going on. We've got some pretty high values here. And we've got acoustic impedance, which is once again looking bimodal. All right, so I hope that this was helpful to you. Just a basic walkthrough of how to display univariate statistical distributions in Python. Once again, if you're interested in using this type of methodology, you want to try it out, you can go ahead and just go to my GitHub account and you'll find lots of demos like this one. This was specifically the one on the geostats pi data distributions, but of course there's many other types of workflows that show you how to do things in Python, statistical analysis to support subsurface and spatial analysis. I hope this was useful. I'm Michael Perch. I'm an associate professor with the University of Texas at Austin. I'm also on Twitter, Geostats Guy, GitHub, as you just saw, Geostats Guy, Geostat Guy lectures, and I'm happy to discuss. And if you want me to come visit you in your company, I do a lot of teaching and training, mentoring, project review, and so forth. So, all right, everybody take care. See ya. Bye.